In this lesson, I'll demonstrate how vectors in a set are linearly dependent. This is part 2. Consider the set of vectors given below. We have 3 vectors and they have an x, y, and z component. We have to show that they form a linearly dependent set, and B, write one of these vectors as a linear combination of the other. Before we begin, we discussed in part 1 that a set of vectors is said to be linearly dependent if a vector in that set can be expressed as a linear combination of the others. Otherwise, the set is said to be linearly independent. So how do we express it as a linear combination? Well, we'll take each of these vectors, multiply it by a scalar, and set that equal to 0. So let's go ahead and do that. We'll take the scalar k, k1, and multiply it to the first vector, 1, 0, and -1. We'll introduce another scalar, k2, and multiply it to vector 2. And similarly, we'll take a third scalar, multiply it to vector 3, and that should equal to 0. Now, if we can find a value for k1, k2, and k3 other than 0, that means it's linearly dependent. Otherwise, if k1 through 3 are all 0, then it's linearly independent. From this point, we want to create 3 equations. Our first equation will relate all the x components. So we have k sub 1 times 1, k sub 2 times -1, so I'll write down negative k sub 2, and k sub 3 times 1 is k sub 3, so I'll write down k sub 3 is equal to 0. That's our 0 vector. The second equation will relate all the y components. So k sub 1 times 0 is 0, it's nothing. Over here we'll have 2k sub 2, and over here plus k sub 3 is equal to 0. Finally, the last equation relates the z components. Negative k sub 1 minus k sub 2, because k sub 2 is being multiplied to -1. There's no k sub 3 here, and we'll make that equal to 0. So now I'll create a matrix out of these equations. My matrix should look like this. I'll have in the first row 1, -1, 1, and 0. In the second row, 0, 2, 1, and 0. -1, -1, 0, and 0. Now that we have our matrix, we can go ahead and solve it using any method that you like. I'll try to put this in row-reduced form. And to do that, I have to make this -1 into a 0, that into a 0, and eventually solve. So first, I'll add row 1 and row 3 together, and that will serve as my new row 3. If I do that correctly, I should have a matrix that looks like this. The next thing that I want to do is make this 2 into a 1, and I can do that by dividing row 2 by half, or multiplying it by a factor of 1/2. That becomes a 1, that becomes half. Lastly, I want to make the 2 in row 3 equal to 0, and I can do that by subtracting 2 times row 2 from row 3. So let me document that. Now that I've written this down, I can go ahead and find out my new row 3. If you do it correctly, your matrix should look like this. Now notice the matrix that we have has less equations than unknowns. If you have a matrix with less equations than you have unknowns, this means that we'll have an infinite amount of answers. Not only does that prove that this is linearly dependent, it also tells us that we're going to have non-trivial answers. Trivial answers would be k sub 1, k sub 2, and k sub 3 being equal to 0. And that would suggest that it's linearly independent, which it is not. So how do we find out what k sub 1, sub 2, and sub 3 are given what we have? Well, we can convert this row back into an equation. We have k sub 2 plus half k sub 3 is equal to 0. I'm going to solve for k sub 2 by bringing that over. I get k sub 2 is equal to -1 over 2 k sub 3. I'll highlight this for clarity. And in that first row, I can convert that into k sub 1 minus k sub 2 plus k sub 3 is equal to 0. Bringing that over and that over, we get k sub 1 is equal to k sub 2 minus k sub 3. Substituting this into there, I'll end up with k sub 1 is equal to -1 over 2 k sub 3 minus k sub 3. Subtracting the coefficients, we end up with -3 over 2 k sub 3 is equal to k sub 1. So at this point, we can choose any value for k sub 3, and we will end up with new solutions each time. For example, if I set it equal to 2, I'll get a k sub 1 that's negative 3 and a k sub 2 that's negative 1. So we would take these values and substitute them into here, here, and here, and we can make one vector equal to a combination of the other two vectors as a result of that. And there you have it. That is how to show that vectors in a set are linearly dependent.